Okay, so the question 11 was about radioactive decay. And so the first thing it was asking to explain why radioactive decay is random and spontaneous. So for each of them, I get 1 mark. So random, basically radioactive decay, we cannot predict when a nucleus will decay. We also can't predict which nuclei will decay. So if you said either or all of those, so can't predict which nuclei will decay, or you can't predict when a nuclei decay, you got a mark for saying it was random. Spontaneous is a little bit different. Spontaneous basically means it's not affected by or influenced, or you could have said modified in any other way. Okay, essentially things like if we heat it up, it doesn't change it, and if I put extra pressure on, it doesn't change it. It is spontaneous, it just happens. But the IB is saying here that decay is not influenced in any other way, it's not affected in any other way, it's not modified in any other way, is the terminology they were using in their mark scheme for that second mark there. The next question then was all about the binding energy of a nuclei. So we have uranium-238 and it undergoes alpha decay to form thorium-234. So we've got uranium going to an alpha plus our thorium, so that should be TH for thorium. And we've been given the energy that's being released in the decay, the binding energy per nucleon for the helium, and the binding nucleon for thorium. Remember, helium is an alpha particle, helium nuclei, so we can recognise that one up there. So this question, I had to be thinking about my binding energy before and my binding energy after, and also the energy release that's taking place in there. So what I did was I got a mark, and you got 1 mark for doing one of these. Okay, so I worked out the total binding energy of thorium, so 7.6 multiplied by my number of nuclei, so 234. So 234 multiplied by 7.6 to give me 1178.4 mega electron volts. Or I could have had a mark for showing it for the alpha. You didn't get 2 marks for doing this separately, you got 1 for just showing one of them. So in this case I did helium. Now helium nuclei, remember, is 42, so it's 4 in this case is our atomic mass number. Multiplied by 7.07. So in this case, I get 28.28 mega electron volts. So the combination of the two, I just want to add those together, is 1806.68. So that's my mega electron volts of my total binding energy afterwards. So my binding energy before, I'm going to do my binding energy after, I keep saying divided, minus my energy that's being released. Okay, so I've got 1806.68 minus 4.27, which is up here, to give me 1802.41. Now that is the binding energy of the of the uranium. But this is looking at asking for the binding energy per nucleon. Okay, so I can't really stop here. So I get 1 mark for getting to this point, and if you left it there, you didn't get any further marks. So to do the binding energy per nucleon, I needed to then divide it by the number of nucleons, so 238 in this case, which gave me 7.57, and again 7.57 mega electron volts. A nice little tip for this as well is when you're looking at these binding energy per nucleons, okay, with something like thorium and uranium, you would expect those answers to be quite close. Okay, so you think about our binding energy per nucleon curve, they're not too far away. If we kind of look at that curve when it goes up, okay, so they would be quite similar in their values up there. All right, you would expect it to definitely not be close to the helium one, but you would expect it to be close to the thorium. So it gives you a little kind of last quick check that you can make sure you're in the right guidance for this. For 11C, this was quite a tricky question, and it took me a little bit of a while to figure this out. So kind of hopefully you understand this explanation, but we're doing the ratio of the kinetic energy of the alpha particle versus the kinetic energy of the thorium nucleus. So we could do half mv squared in this case. Now I don't really know anything except the binding energy or the mass numbers of the nuclei here. So I was trying to think, well, I haven't got velocity, so how can I maybe get rid of velocity? And I'm thinking in terms of like a decay, there's like a collision that's taking place in terms of like, not collision, sorry. In this case, we've got some sort of division happening, so we're going to have a conservation of momentum taking place, so we've got momentum is equal to mass times velocity. So kinetic energy, I could say here, rather than saying mv squared, I could do momentum squared divided by mass. So that gets rid of my mass out of this squaring, and then I've got my half in. So I can say kinetic energy is equal to momentum squared divided by 2m. Okay, so in this case, if I've got kinetic energy of the alpha divided by kinetic energy of thorium. I've got the momentum squared over 2 mass of the alpha divided by the momentum squared divided by 2 mass of the thorium. Well, again, we've got both of them being split, being like repelled out, so we've got their momentums being conserved, so I can get rid of these 2, so I can cancel them. I can also cancel the 2's, so I'm left with, when we do our fractions, this one comes up, mass of thorium divided by mass of alpha, which I've got values for because I can use their atomic mass number because it's just a ratio. So I would do 234 divided by 4, and that gave me 58.5 for my final mark. This one, I'm not going to lie, it took me quite a while to do this one, so it was a bit of a trickier question, so well done if you got this one.